Today we're going to be looking at the Unit 3 review. Now this is the last unit of Term 1, and it's all about scatter plots and linear regression and residuals. So number 1, Jimmy John's sales team is collecting data for their marketing department. For an entire year, they have recorded the total amount of deliveries and the outside temperature. Question is, what is the explanatory variable in the situation? What is the response variable? And how do you know? So remember, the explanatory variable is the thing that we really can't control. It affects the other thing. So our two things that we kept track of was the outside temperature and amount of deliveries. Well, if we think about it, does deliveries, the number of deliveries affect the temperature, or does the temperature affect the deliveries? Well, outside temperature would be our explanatory variable then. As it affects deliveries. Meaning our response variable is deliveries. And then to answer the last question of how do you know, weather affects the deliveries. Next one, for 2 through 3. A statistician at St. Ambrose was interested in the commutes of their professors. They recorded the total number or the total distance each professor rode their bike to campus each week and how long it took them to get to St. Ambrose. Below is the scatter plot and residual plot for the data they found. So on the left we have the scatter plot, on the right we have the residual. So then question 2, the regression equation is y hat equals 0.667x plus 2.01, where y hat is how long the professor is predicted to ride, and x is the distance they have to ride the entire week. One professor they talked to rode a total of 16.5 miles and took 11 hours. Use the regression equation to calculate the value of the residual for this person. So we're going to need to find a residual, meaning we're going to need to do y minus y hat. Where y is what actually happened, y hat is what's predicted. Know what happened. We need to find our residual then. So we're going to plug in the 16.5 in for our x. So we can write y hat equals 0.667 times 16.5 plus 2.01. Doing so, we end up finding out the y hat is 13.0155. So we found the predicted value. We need to find our residual then. So we're going to do y minus y hat. Well, it took them 11 hours. So it's going to be 11 minus predicted 13.0155. And we end up getting negative 2.0155. So our residual is negative 2.0155. Question 3 has two parts to it. First, we are going to circle the point that represents the professor in question 2 on the scatter plot and on the residual. So the scatter plots, what actually happened, they took 11 hours to ride 16.5 miles. So length in miles, we go over to 16.5 roughly, and we go up to 11. So it is roughly that point. For the residual plot, we go over to roughly the 16, and it did get squished at the end. Going over 16 and up to our 0 line. The residual was negative 2.01, so it's slightly below negative 2. So there's our point. Second part of the question. What additional information does the residual provide about the couple in this, well, about the professor, I meant to say, in this situation? So, we can say it is below the predicted line. Next. For number 4 through 8, a student wonders if the hours of sleep you get correlates to the test scores on tests. They decided to record the number of hours their friends sleep and the scores of their upcoming test. 4 wants us to create a scatter plot. Now, one thing that I notice, 6 through 6, 4, 6.5, 8, 7, 5.5, those are relatively small numbers. And looking at our graph, we have 10 lines, so we can just count by ones. So I call my x-axis sleep. And I just count by ones. Our y-axis is percent, or their test score, and that's a lot higher. In fact, the smallest one is 58, and once again, we only have 10 lines. So, remember, we have the ability to put in that heartbeat thing to show that we're scrunching up those numbers and not starting at 1. So I want to choose cut by tens. So 50, 60, 70, 80, 90, 100. We don't have any over 100, so I'm not going to worry about that. And now we're just going to plot our points. So the first one is 676. Oh, roughly here. 458. 6.5, 70. 898. 781. And 5.5, 65. So there is our scatter plot. Question 5. Describe the strength, direction, and form of the scatter plot. So remember, this is the part where you type the numbers into your graphing calculator. Remember, you're going to do second 0, go down to diagnostic on, and hit enter. Then you're going to hit stat, hit enter, and put your x's in L1 and your y's in L2. Then you're going to hit second mode to quit out, hit stat, move over to calculate, and then you're going to choose number 4. And then remember, your correlation coefficient is your R value. So for this problem, don't just tell us the strength, direction, and form, give us the value as well. So we end up getting 0.92916, blah, blah, blah. So then we're going to use our number line, the one that went from -1 to +1, and see where this falls. All this falls under strong, positive, linear. And that is our strength, direction, and form. Strength is strong, direction is positive, and form is linear. Six and 7 deals with the ideas of extrapolation and interpolation. Remember, extrapolation is a value outside of our range. Interpolation is a value inside of our range. So if we look back at our x values, our smallest was 4 and our largest was 8. So if we chose a value between 4 and 8, that would be an interpolation. If we chose a value smaller than 4 or bigger than 8, meaning beyond our range, that would be an extrapolation. So for example, for an extrapolation, I could say they studied for 10 hours and they got 100%. So there would be an extrapolation, and extrapolations are never accurate because we don't know, outside of what the data looks like, what happens. Because the small part that we graphed might be linear, but the stuff before the 4 or after the 10 doesn't necessarily have to be linear. It could be exponential where it curves. It could change directions and become negative. Interpolation, an example, we could say they studied for 5 hours and they got, let's say, a 70%. That would be a good prediction because it's based within the range of what we know. We know what happens, what it should look like between 4 and 8 hours. And this falls in line with that. Number 8, West's gym teachers gave a physical fitness test to all of their students, then had each student fill out a survey about their thoughts on school. The teachers found that there was a moderate positive correlation between the two. Explain why it would not be possible to conclude from the study that a student's physical fitness increases their positive thoughts about school. So this is saying that there is a relation between what students think about school and their physical fitness. However, does that mean that the more you work out, the happier you're going to like school? Not really. So what this means, correlation does not mean causation. So just because something is related does not mean the first thing causes the second thing, or vice versa. For 9 through 10, weather data was recorded for a sample of Iowan cities in 1 year. Variables measured included January high temperature in degrees Fahrenheit, January low temperature in degrees Fahrenheit, annual precipitation in inches, and annual snow accumulation. The relationships for 3 pairs of variables are shown in the graphs below: January low temperature in graph A, precipitation in graph B, and annual snow accumulation in graph C. Question 9 says, identify each graph if it is best modeled by a linear, quadratic, or exponential function. So, looking at the graphs for graph A, I notice pretty much all goes in the same direction in a nice kind of line. So I could say graph A is linear. Looking at graph B, kind of follows a U shape. So that curve in it that goes completely changes directions is a quadratic. So I'll say graph B is a quadratic. And then graph C. A little bit harder to see because the values are spread out, but does have a bend in it. So because it has a bend in it, not a curve like in graph B, graph C is exponential. Question 10, for which pair of variables does it make sense to use a correlation coefficient? Graph A, graph B, or graph C, and defend your choice. So if you remember back to the definition of correlation coefficient, in its own definition, it says a relationship between a linear relationship. So the only linear relationship that we had was graph A. So it's only for linear relationships. "11. Suppose the spread of a rumor amongst 500 high school students was recorded. In the following least squares regression line was found. Y hat equals 7.3 plus 0.5x, which I'm going to rewrite as y hat equals 0.5x plus 7.3, where y hat is the predicted number of people who has heard the rumor, and x is the time the rumor has spread in minutes. Interpret the slope and the y-intercept of the regression equation in context." So, to interpret slope, as the explanatory variable, so as the time increases, so as time, pardon that, smartboard's all messed up today. So as time that the rumor has spread, increases by 1. The number of people who has heard the rumor increases or changes by our 0.5, that slope. Y-intercept or initial value. So this is, we started with 7.3 people hearing the rumor. Last page. For 12 through 16, Iowa Board of Educational Examiners is curious about if having smaller class sizes matter. They decide to survey various classrooms across Iowa to compare the number of students in the classes and the average grade of the students. Their data appears in the table below. So, we need to figure out what affects what. So our explanatory variable and response variable. Well, class sizes, they say, is affecting grade, so class sizes is our x, grade is our y. So I will label that. So class size and grade. Now for the class sizes, we ranged from 3 all the way up to 40. So I can count by 5s. For our grade, ranges from about 45 to 100. So I want to do the heartbeat thing again. So I can start at 45 and I'll probably count by 5s again. And then this is just going to be rough placements. And I'll do a few of them. So 33, 67, and 18, and 82. 35, and 52. I'll do one more. 15 and 80. So then you'd spend the time plotting all of the other points on the graph, just like how we did before. 13, calculate and interpret the correlation coefficient. So once again, you type the numbers in the calculator. L1 is your class size, L2 is your grade. And we will find out that it is a negative 0.9033. So then what does that mean? Well, it is a strong negative linear correlation. On that same screen as your correlation coefficient, it tells you the equation for the least squares regression line. So that would be your y hat equals ax plus b. And you would replace a and b. So you should end up getting y hat equals negative 1.3119 blah 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 x plus 104.2915 blah blah blah. Using the regression equation, predict the average score of a class that has 14 students. So we're going to plug 14 in for our x. So y hat equals negative 1.3199 times 14 plus 104.2915. Doing so, we roughly get 85.9249 blah blah blah. So then 16 is asking, is a prediction in number 14, so it meant to say the previous problem, an extrapolation. Explain. So the value that we plugged in is 14. Our range of values went from 3 to 40. 14 is within that range, so no, it's not an extrapolation. 14 is in the range. Of 3 to 40.